to kiss, baby.
Masikhohlwe ngenkinga sekukubalisela
How'd you?
masikhuphula imizwa
Wezombi.
sukumisa umzimba
NTA,
masikhohlwe ngenkinga sekukubalisela masikhuphula imizwa sukumisa umzimba Koma sava, na aye sava, na
Comment ça va? Comment ça va? Comment ça va? Comment ça va? Aya ça va.
aye sava,
Aya ça va. Aya ça va. Aya ça va.
Koma sava.
Zombie, this it just be buggy. Zombie, this it just be buggy. How are you? Unjani? Como vai? Habari gani? Ni hao. Assalamu alaikum. Como estás, amigo? Namaste. Como ça va? Comment ça va? Comment ça va? Comment ça va? Aya ça va.
Aye sava,
Aya ça va. Aya ça va. Aya ça va.
Koma sava, unyaka savana, chiga bonu yayithethela, wente shot nyamthatha, asa, ay manu yasakuna nangat ngamshaya ngebhathabhak, athi koma savana mina ngisithandela istenso ima, masikhohlwe ngenkinga, sekubalisela, masikhuphula imizwa, sukumisa umzimba.
Kufosi ni ujinga, sikutaka kwenda, yani ni kujiumiza, nimeatai kupenda.
Koma sava,
Comment ça va?
koma sava,
Comment ça va?
koma sava.
Comment ça va?
Hello and welcome in, everyone. I hope you're all doing well today and sort of get started with today's session. So, we're first going to start off with our agenda, which will cover the rules of engagement. We'll then hop over to the main session, which will be run by myself. We'll then have some Q&A and then sort of pause for updates and announcements from the ALX team. So in terms of rules on engagement, if you do have any questions, please post them either onto Slido or onto AnswerBase. Chat will be opened, sort of ad hoc to interact with the tutors and myself. And most importantly, listen, learn, and share. I'm going to pause on the screen for a second. So this is going to take you through to the Slido link. So grab your phone, and if you do have any questions, please pop them over there, and we can then have a look and answer them at the end of the session. All right, cool. So link is also in the chat, but without further ado, we're going to sort of look into our main session for today. So over the last week, you guys sort of have delved into the realms of unsupervised learning. We spoke from a very theoretical point of view, what these various models are. We looked at the sort of applications that they can exist in. And today I sort of wanted to take it back a bit and just relook at sort of the functional principles behind them. So how do we execute it within a notebook, all the way through to understand basically what makes these models tick, how you should choose these models, and then how they work on paper. So looking at the code notebook will be popped into the chat at sort of the end of the session for you to have a look at and play around with the notebook. And then obviously, how do you interpret these results that are coming through, right? So it'll be very basic. We're not going to go into the maths just yet. It's, I think, still too early to go in that space, but look at the code, and then basically what I want you to see is how we make these thought processes as we go through this journey. So our basic imports, nothing crazy on this front. Pandas, Seaborn, and Matplot. These are just some basic sort of imports to get us started. It's none of the clustering or dimensionality reduction dataset. It's just the principles. Now we are using a dataset that you will probably have interacted with or will interact with. Reason we chose this is it's a relatively decent data set. It's still relatively small in the sense that it's only about, I'd say about 2,000 or so data points, which isn't a lot, but it does give us the opportunity to view a data set without a predictive variable. So with that sort of in mind, what we're looking to say is, well, if we've got this data set, we have no predictive variable, where does the unsupervised learning come in? So we know that unsupervised learning, from a definition point of view, was aimed for us to find patterns, discover certain themes, or reduce the amount of features we have. So we're looking at the main and important numbers. But if we don't know what they are, we need to uncover that first. So if that's the case, let's look at sort of this data set holistically. We've got a wine data set. So we've got sort of the alcohol, we've got the malic acid, ash in it, magnesium levels, flavonoids, color intensity, the hue of it, which is the color and spectrum of that given wine that's coming out, all the way through to sort of Proline. Now, for those that aren't familiar with wine, often you've got red and white wine and sort of distinct colors there, right? So one is quite clear, the other one is often just this quite a rich red color. And between the two is often like a sweeter one, which looks a lot like a pale pink. But those are sort of your wines that exist, right? So your someone is a fellow drinker said rosé exists, right? So between those spectrums of white, red, and your rosés, those are your three sort of wine categories that you would expect. And without knowing much about the data set, the color intensity and hue, which is basically the like shade of color, should technically be able to tell us what wine it is without looking at any of the other indicators, right? So depending on the color spectrum, we can then say that this is a white wine, red wine. Now, obviously, this data set doesn't have that labels attached. So imagine now if we wanted to create clusters, we would hope that we find 3 distinct clusters that form, hopefully, or 2 at least. And our journey is to then find the best way to do that, right? So that's obviously we've got knowledge of the data set. However, if we don't know that, how does it look to go down this journey of analyzing this data set? So firstly, we'll start off with a basic describe. So obviously we want to see how many data points we have on average, our means, and focusing on sort of our variables that probably will be the most important to us is color intensity is on a scale of pretty much what we're looking at 1 all the way to 13, and then you've got a hue which starts at sort of 0.58 all the way to 1.71, right? So we've got those indicators. The other variables all seem to be relatively make sense. We do have one variable that is out of the normal. So most of these values are all under 100, right, in terms of their average. However, Proline is above that. So you can imagine that when comparing this, Proline will be a bit obscured for most of the analysis. So we would need to do some sort of standardization so that Proline fits into the general consensus of all the other data points. As a safety check, we always just check if there is any missing values in our data set. And if there were, we would need to either remove them or alternatively impute them, right? And as we've discussed historically, we decide on a case-by-case basis what we're looking to do. In the realm of unsupervised, it's relatively safe to go and impute the data because at the end of the day, you don't have a definitive label. You're just trying to understand the data. So it should not obscure the models too much by putting in synthetic data, but it is again handled on a case-by-case basis. But it is often less of an issue to impute in unsupervised than it would in a supervised algorithm where the labels are known. And obviously every indicator going into defining that label plays a critical role often when predicting what class something belongs to or the value that you're looking to assess. But in unsupervised, it's just patterns, right? So it's a magnitude of things coming together to find sort of commonality between features. and sort of other respective data points in your data set. Our data types, a safety check just to ensure we are working with numerics. If we were working with any text data, you would imagine that we would need to use some NLP to process that, bring it down to a numerical level that we can then interpret and process by the machine itself, right? And last sort of check is a correlation matrix. Now, this one will just pause for a second to look at sort of the various components, right? Now, normally we would look at a correlation matrix to say, well, how well does the variable correlate with our predictive variable? But we don't have that predictive variable. So what we're looking for is how similar is the data points to one another? Is there any sort of collinearity that could exist in the space? And we can then look and evaluate that. Now, obviously, the closer it is to red, we've got similarities that are coming through. So in the likes of your, I'll zoom out just a bit so we can get that. So your flavonoid is very similar to your total, phenols, right? And that's very high correlation between these two, right? So in this case, some may argue that you wanted to remove those because they're similar, but we're not looking at regression, right? We're not doing any predictive analysis. We're not forecasting, which means these issues of collinearity and stuff shouldn't be an issue. However, if we did want to make one of these our predictive variables, we need to make a very smart decision to whether we keep something of that nature in the data set or we remove it, right? And depending on the type of models you use, you should now have enough context to make a decision, or if not, Google to see how certain models react to collinear data and so forth. Right. So generally, everything seems to be relatively correlated decently with each other. There are some mostly negative trends. So you'll notice that most of the colors on the spectrum is blue, meaning that it's an inverse relationship between each other, meaning there's sort of a negative trend that's happening, right? So everything sort of has a negative slope to it, which when we plot these, you should see the same cause and effect, depending on which value you put on your X and Y axis. Right. Now, this is just a reminder of how to look at your distributions, right? So typically you would do it for every single data point. That is a lot in this case because we have 13 columns. So I just took 5 as an example. And if you want to change any of these when you get the notebook, simply edit the column names here and you will then be able to see different sort of distributions. And what are we looking for in a distribution? We're looking to see, is it normally distributed, which will indicate a sort of linear relationship, one that we can model quite comfortably, which helps with linear assumptions. However, if things are obscured and skewed, we can imagine that the model is going to struggle with linear relationships as it's not something evident in the underlying data set. Now, important note here is that all these distributions are based on raw data. Once we standardize this, you can imagine that you're going to then have issues where it's not going to look the same. These distributions will change, and generally through standardization, you should see better distributions forming and stuff centered a lot more around the mean. So as I said, when the notebook is shared at the end of the session, take it, break it apart, and have fun with changing this and looking at the different distributions of these columns. Right. Now, the next one is a sort of pairwise scatter plot, and we will look at this visual again because it's very important in sort of the long run as we look to see, is the data linear or non-linear? And if you guys remember, how do we test that? Well, look to see if you can walk a line or plot a line through the data points, right? So we're looking at sort of the sort of malic acid. It looks to be a relatively, if you want to try and get as many of the data points, as sort of a positive up. And while we're saying positive up, it doesn't mean that the relationship is guaranteed to be positive. Because we don't have a predictive variable, we're not plotting to some independent and dependent place. So depending on which value you choose to put as your X and Y, this can be interpreted differently. All that we're looking here to see is if I take a line can I draw some sort of equation out that fits through our data points? And if not, if it just looks like a straight line, then probably nothing worth it. But if it does have a slope, we've got some sort of linearity that exists. So that is what we're looking for in this pairwise. And you would evaluate each and every combination of the data set to see. And obviously, I just focused on the top 5 points from above. But if you do want to look at all of them, that is up to you, right? But as I can say, going through 13 plots makes this graph very small, but we are going to look at it later to exactly explain why we use this graph and why it's important. Cool. But at this point, I'm going to pause and let you look at this graph and tell me if you see any linear relationships in the data, right? Does alcohol and magnesium have it? Does magnesium and methylis? And you can look at each and every one of these and try to see in your mind and conceptualize it. Do you see any linear trends, right? Let's see what your answers are just of these variables, right? See if there's something and just remember your answers. You can put it in chat as well. Note that you might change your answer a little bit later on, but for now, what patterns do you see? And note we're only looking at sort of 5 columns for now. We can look at more with changing that code itself. Cool. A lot of people sort of ash and magnesium seems to be the easiest one. Big cluster there, a decent line from there to there will probably draw quite a nice linear relationship there. There's a slight one in sort of ash thing, but obviously visually looking at these data points, you can imagine it's a bit of a touch and go. And there's also a nice one for alcohol, which plots across there. Now, as you know, I prefer to use the numerical side of things. So if you were doing something like this, I would highly recommend a t-statistics test and look at sort of the individual correlations from a number perspective. And if it's closer to 1 or -1, you've got some sort of linearity that you can confirm. However, visually, as you know, the human eye will draw lines where it thinks is best, and it's not always statistically correct. So keep that in mind when you guys look at this, is that there is a better way to do it than this graph. These graphs just look good and sort of show you a nice distribution of your data, which often a number can't show you, but the number is definitely more accurate to tell you if there's a linear relationship or not. Okay, so last thing that we sort of go to check, right, is a box plot. Now, I deliberately dropped Proline out just because Proline, as I mentioned, the mean was quite obscured, which means we couldn't really get a good view of the data. Now, if this is not something you want to do, what are you going to do to change the code? In this block of code that you're looking now, where it says data is equal to df temp, if you substitute that with data, you will then see the original data set without me dropping the Proline feature. So with that in mind, this is our box plot, and we're going to zoom out because obviously it's relatively quite big. Now, in this case, you can look at sort of each and every one of the variables. There's a move about. Dots indicate our outliers. Your first line, second line is your min, your max, your median, and sort of your interquartile ranges are all indicated. You can obviously drop magnesium if you want, and then just focus on everything between sort of 0 and 20, and you should then see a little bit of more spacing between the data. So again, up to you in terms of how you want to drop and analyze this, but the whole point of this graph is just to see, is there any obscured data points? Now, the question I have for you in chat is, what should we do with the outliers in unsupervised learning, right? We know what we did in classification and regression, right? Depending on how basic the model was in regression, we'd need to remove the outlier in order for our model to become more generic and better fitting for our general data points. However, a more advanced model was able to process outliers a bit better. So my question to you is, when we're looking at unsupervised, does that theory apply? Yes, no. Do you think we drop outliers? Do you think we keep outliers? What do you think would be the optimum thing to do with outliers in unsupervised, based off what we've discussed over the last few weeks? Trim it, You neaten them up so there's no outliers. That could be a thing. Keep the outliers. Keep. Right. Dimensionality reduction. Seems like we've got some good thoughts here now. So if you trim it, right? So the whole point of like unsupervised, if you look at like its application point, is it's for like fraud detection, anomalies, right? We're looking to find obscured patterns. And technically, outliers are patterns that are obscured, right? We want to see these weird points. Now, a good point that's sort of coming that I think sort of let's go give the credit to the person that said it first. I think it was Cow. You were going to standardize this data, which means that all these outliers will in essence become normal, right? So in essence, us keeping it is probably fine. We won't have too many issues down the line. And sort of as you sort of go and scale this, these outliers become almost null and void. They still exist in the data set, which means when we sort of transform back, you will still observe them, but it's definitely useful for seeing how do they conform within the patterns of the data set and its cause and effect. Next up is a different visual that sort of I want you guys to look at. I'll zoom in on the code for a second. It's nothing too crazy. It's called a cluster map. Now, different to your correlation map, it uses a correlation map to build it. But what it does is it starts to group similar data with each other, right? So obviously based off the correlation coefficients, are they similar? And then groups them together. Now, for those that sort of hopefully got to this material, hopefully you recognize what this is, right? Your dendrogram has appeared. So this is showing you what theoretically would be the optimal clusters should you break down this data set. It's identifying 3 groupings of data, right? You've got your hierarchy cluster that's now formed. And if someone had to ask you how many divisions are there, right? How many clusters can you visually see? Anyone have an answer for how many clusters they can see in this given shape, right? And remember, you as the data scientist can decide how many clusters, right? So is it going to be 2, 5, 3? And theoretically, there's no right or wrong answer here. There is one that, depending on how finicky you're being, you will then interpret this slightly differently. So looking at this cluster map, from my perspective, I would break it into 3 clusters, right? The reason we're doing that is remember to read these graphs. If you want them to be as different from one another, you then look to see the highest point that you can cut your graph. And the highest point that sort of gives us the most difference is a straight line across this point here, right? Hopefully you guys do see my mouse on the screen. Looks like you can. And if you draw a line from there to there, you get 1, 2, 3 clusters. That's because you want them to be more different. However, if you want to be less different and you want your clusters to be a bit more similar, you bring your cutting line slightly lower. So if you bring it slightly lower and you draw it here, you can get 1, 2, 3, 4 different clusters. Bring it even further, you can get a different array of clusters. So this visual is quite a nice one in the sense that you'll notice it orders all the columns differently to your correlation matrix, and then sort of gives you a view of how well these 3 variables seem to be correlated with one another. These variables are correlated with each other, these 3 and these 2. So it just gives you a good view and sort of shape of the data set that you're working on, how well each data point is correlated with the other. So as I said, there is no right or wrong way. You can go all the way to say there's 13 clusters to some degree, because in fact you can. If you draw the line right at the bottom, there's 13 different clusters that can form because of each individual column can form a cluster. So again, up to the data science point of view, how similar or dissimilar you want things to be is then how high you draw your cutting line. All right, but from my perspective, I would cut it as high as possible, which would be 3 clusters that then form So we have three distinctive groups. So we're hoping to see three clusters. Now we need to wait to see what the data has to tell. Right. So welcome to sort of PCA and then your TISNI, right? Now, principal component analysis speaks to assumptions that our data is linear relationship amongst variable. So as we sort of spoke and looked at that pairwise plot, we need to look, is there relationships between these variables? Are they linearly related? If not, PCA is not going to work, right? How it works is our goal is to reduce the dimensionality of the data set. So instead of us comparing 13 columns, we're going to drop it down to 2. And that's often then where we look at the scenario example, which is visualizing high dimensionality data, which is the wine data, into 2D or 3D, right? So 2D would just be two shapes or columns that we assess, which is often known as PCA1 and PCA2. Alternatively, we can add a third dimension to this, which will create depth in our analytics. But for most cases, what I recommend is you do a 2D visualization because the human struggles to visualize 3D on a sort of flat space. Now, your TISNI, right? So your distributed stochastic neighbor embedding, the assumption is that there is no sort of distribution, right? So it means that you can throw whatever you want. It doesn't have to be linear. It can just be any data points. How it works on the difference of the alternative approach of sort of PCA is that we look to model the pairwise similarity at a high dimension data and low data embedding. So it's sort of a dual approach. And the scenario here is that you create a 2D map, right? Identifying clusters visually. So in both cases, we should get this visualization showing us two, in essence, clusters that are forming from PCA and TISNI. Our first approach is we need to standardize our data. And someone mentioned that earlier, so well done for remembering. We need to standardize it so that all the data is on the same scale, because obviously if we're going to flatten everything to 2D, they need to all be on the same scale. If they're on different scales, we cannot effectively do the sort of visual approach of a 2D visualization. So if you don't do the step, which I'm going to actually recommend, do it and see what happens. So skip this entire step and just use normal data. Look at how different the visual comes out. It's not as interpretable. It's a bit more difficult to read, and it often doesn't make sense because you're now working with multiple scales. So, as I said, we bring back the Pearson thing, and obviously it's a lot to look at. So we can just look at sort of the top row if you want. For each and every one of these, I guess, visuals, does it look to be something linear happening? Right? From your perspective, some of them look like there's linearity. And if you have to count exactly how many look like there's a linear trend, right? There's sort of this one, right, which is a poor one, but there is a linear trend there. This one, also second linear trend. 2. This one, no linear trend. Third one, linear. No linear trend. No linear trend. No linear trend. Nothing here. There is a linear trend there. Nothing, nothing, and a linear trend. So across all the data points, there are some that indicate a level of linearity where others don't, right? And obviously you could just go and look at it any other way, but it's the same thing because in essence, we're mapping every single one to every other data point. So you can obviously spend a lot of time working on this to see the relationship, but overall, it's very mixed readings. So it's not consistent, meaning that typically this data set is leaning more to sort of being non-linear in nature. But there is enough evidence in between to suggest that there are some similarities that can help us with our analytics, right? Like I said, it's a very chaotic graph, and you can spend quite a bit of time reading this, which in essence is quite shocking, right? So you can imagine spending a lot of time just looking at this graph, trying to see each and individual relationships. Now, you might wonder why there's an error. To be honest, I don't know. The code ran fine and I got an output, so not too sure why that error exists, but you should be fine when you run the notebook as well. Right, So starting off with PCA, right? To run and execute the code, in this case, we said that our PCA is 2 components. We can increase this, and you can imagine that increasing PCA is going to create another dimension. So 2 is our stock standard approach, which creates a 2-dimensional view of our data. If you wanted to create more dimensions, 3, 4, 5, change it there, but certain pieces of code need to update. You'll then need to update your columns to reflect the additional PCAs that you are creating. And then you'll need to ensure that your sort of scatter plot accounts for your extra dimensionalities that you're bringing in. And this is then what forms, right? A graph that looks like this. Now, if I had to ask you guys, what do you see in this particular graph? I'm happy to hear your thoughts. So while you're writing it in chat, what do you see? Do you see a pattern? Do you not see a pattern, right? Take some time to absorb it. And sort of, what do you see? Is there any groupings, right? Someone sees a bell curve, right? Just a little hill, if you want, curve pattern of the data set, right? You can probably get very creative with the patterns that you're seeing, right? Right? We could add labels, right? Someone says they can see 3 clusters. I'd love to know where they are. I'm assuming probably one there, somewhere there, maybe there, right? So the colors themselves, there's no difference, right? But in essence, it looks quite unfamiliar. It's not an easy thing to just say there's 3 clusters that are formed, or that there's 2 distinguished clusters, right? Obviously, if you spend a bit more time, which some of you guys are doing now, there's obviously a negative hemisphere. There is a positive realm, and then the negative and positive realm, right, that you can focus on. So in essence, you could have 3 quadrants that in essence would form in the space, the positive range, negative range, and sort of the dual range of positive and negative. So those exist, and we can now take it forward and say, well, potentially there are 3 clusters. So explaining what happened here. So PCA, we're looking at the variance, right? The first principal component captures the most variance in the data set, right? So principal 1, right? Hence, from this point to that point, you've got a sort of scale of -4 to 4, right? It's slightly broader. Each subsequent component captures the remaining variance in descending order, right? So you find every single thing else, and then you find the difference between those data points. Right, a scatter plot of 1 and 2 will show you how well the data can be represented in a 2D space. If your data cannot segment in the space, it means that the data set might be quite complex or doesn't lean to PCA, right? And as we said, PCA needs linear data to create good breaks. So if it can't do it, means this data set's not linear, meaning you should not use PCA to reduce the number of features. Now, from a clusters and patterns, the question we have is, if the clusters are visible, we can say we've got groups of observations which can become features for us later on. If there's any overlapping points or lack of clear clusters, this suggests that the linear relationship alone might not capture the complexity of the structure of this data set, right? It doesn't mean that this doesn't work in other data sets. It means for this given data set, PCA might not be your go-to character. So let's look at t-SNE, right? So again, we start off, we want 2 components for the 2D shape. Like I said, the code will be available later. We're focusing more on just the sort of reading and interpretability of these. And now we get the following. And now I'm going to ask the same question again. What do you see, right? And I'm hoping it's a different shape, right? There's sort of some linear relationship, I guess you could go with that. But what we do see is 3 distinct classes, right? It's far easier to see this, right? 3 distinctive clusters, the negative realm, the mid-range, and then the upper end, right? So in this case scenario, this data set, as we saw when we were looking at the sort of pairwise function, which I'm going to go to very quickly. Not all of this was linear, meaning it wasn't the best linear data set to work with, meaning that by theory, Tisney should have done better. And it did. You've got 3 distinct groups, which is what we fundamentally wanted to see at the start. When we spoke about the wine, we knew we needed to see 3 types of wine, which we are now seeing in Tisney, meaning that there is a way for us to understand and group this data better. So, talking to Tisney quickly, right? The clusters in Tisney indicate the groups observed are similar to each other, right? It's an effective for very high dimensional data to find your local neighbors. An interpretation of this, right? So the points that are closer together obviously share similarities. And the main thing is sort of be careful for over-interpreting the distance between this. So you can see they look quite far apart. It's the important thing to note is that while this is very far apart, when we looked at it from a different perspective, these points were actually a lot closer than normal. So Tisney does have an effect of changing the way it looks in groups, but that is not always a negative. So the main reason we're just telling you guys here is to be cautious of it, but not to be worried about it in the sense that it's wrong readings, just to be careful when you're interpreting it. Cool. And if we want to compare them side by side, this is what it looks like. And obviously, looking at the left, sort of PCA just looks like a very badly drawn Christmas tree. And on the sort of Tisney side, you can see your clusters far more better. It looks more effective to group, and we can now so act more confidently say we've got 3 clusters. So often you might need to run both sets of analytics to interpret these results, but it's up to you to see and test your assumptions and validate them accordingly. And those assumptions are what we stated off right at the start, which I'm going to go to. If the data is linear, then great, PCA will do the work. If there's no inherent distributions that you can read, Tisney should do better, right? So keep that in mind as you sort of look to analyze and work with these 2 processes, right? Great. Now, let's go into k-means clustering. Now, a reminder of just the algorithm steps and then sort of the assumptions. So the algorithm, we initialize a centroid randomly. We assign each point to the nearest centroid, recalculate, and keep on going through step 2 and 3 until we reach convergence. The assumptions in k-means, we assume that each cluster is exactly the same size. What? Okay. Right. We then assume that the data points are spherical and evenly distributed. So in this case, it means that if we draw circles, all the clusters should be the same size and that the data points can fit within a circle. Now, if that's the case and the data looks in that shape, fantastic. But if the data set looks obscured, it looks scattered more and you can't draw definitive circles, then you can imagine you're going to have an issue using k-means clustering. Now, the advantages of this is, well, it's relatively simple to implement and understand, really good for large data sets. The limitations, though, is that depending on where you put your initial centroid, it takes you longer to compute and you could have issues. And then you struggle with data sets that do not have nice shapes and variations. So if your data set is clustered and looks a bit weird, it's not going to be able to do very well on that front. So welcome to our code. Right? In this case, we went with an assumption that k is 5, right? You can change this value, but keep in mind it is again up to you as the analyst to decide what you think is best. And this is something that you'll read over time to see the graph. Now, this is called the elbow plot, right? I know it's going to look a bit weird. The purpose of this is that it is a visual to tell you what your k value should be. So you need to look to where you see an elbow, right? So an elbow is basically when does this graph change, right? When does it magically change directions? So as you can see, it's quite flat, 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 and then it starts to turn. So we're looking for like the turning point, basically the elbow. So imagine an arm, that's the elbow of this graph. So in this case, the elbow is here, which means if we take a line across, it's suggesting that for this given data set, our clustering should be 3, right? The KNN distance should be 3 in terms of the optimal point, right? The data point sorted by distance, this is just sort of the other scale, and we're just looking for that turning point. So our K value is 3, and this indicates then the cluster number that we should choose, right? So often people ask, how many clusters should I put in my data set? Well, to be honest, we don't know until you run this test. You can know from assumptions. Before we even started with this, a lot of you guys were agreeing that there's 3 types of wine, which kind of makes sense. And this has been sort of confirmed in each of the tests that we're running. So in this case, we're going to create our k-means variable data points. And then we're going to do the same thing for dbScan, right? So again, relatively simple code. The 3 comes from here, right? Looking at dbScan, we select an arbitrary point again. We retrieve all points within sort of the EPS distance, which is different to your KNN, which looks at a value of an entire radius, where EPS looks at sort of the smaller microcircles that you can do, which allows you to make creative shapes, which we would have seen when we talked about our first webinar last week, Tuesday. And then you basically create these mini clusters with the sort of sample in mind, and then you mark any other points as noise. So why we don't clean the sort of outliers in the data set is because the dbScan should take it out for us, or at least mark it for us. So the assumptions for this is clusters are dense regions in space, so they all should be grouped quite heavily. We assume that there's no assumption for the number of clusters. In this case, we don't say that there should be 3, 5, 7, 8, 9 clusters. We don't say that there's 3. We let it figure it out for itself. The advantage is you can get arbitrary shapes, so it doesn't have to be circles, and it's robust to outliers. Limitations, the parameter tuning is quite confusing, and if you're not sure, you'll often get clusters of various densities, so it's not always evenly distributed groups. So we can go and create this. Now, how did I get the EPS? I wrote a random number, but I'll explain how to get it correct, right? So I just chose a random number for now, and we can generate these 2 graphs side by side. Again, I'm not focusing on the code. The code will be shared with you. You can look at that later. In terms of the visuals, right, with the RAND, obviously k-means clustering was easy because we had the elbow method. Obviously, I don't need to tell you, but how many clusters do you see? I'm hoping the answer is 3. 3 clusters correlates very similar to all of our previous things. However, dbScan, how many colors can you see on the screen, right? And note that because I didn't choose anything, it just starts to try its own thing. In its opinion, it thinks that there is 1, 2, 3, 4 different types of clusters. Even though the sort of points are close to each other, it doesn't think that they belong together. So how do we fix that, right? And sort of before we get to that, sort of let's just reflect on these. K-means looks really good, right? I mean, we can see great, well-defined and separate clusters. We can check the number of clusters and they are equal to 3, which is exactly what we chose, right? dbScan observed the density, and compared to k-means, dbScan identified just nuisance in the data, just thinks that everything is noisy, and it's not very comfortable with this. So it's not great. So how do we make this dbScan better, or try to? We would in essence take and run this a check to see what is the best EPS score. So the EPS score is what will change this graph. So running this test basically creates something very similar to the elbow plot that you would notice from the sort of previous graph. It looks quite similar. The difference between this is it's tailored for dbScan. While the code might look similar, it's specific around dbScan's distance calculation, right? So it's looking at the distance between each equivalent data points, where the previous elbow method looks at the radius of the cluster, not the distance between each point. So it is a difference between the two, right? Hopefully that makes sense. So this thing, same thing applies, right? It's still the elbow trick. Where is that max hit first, right? There's one there. You can also go sort of 3. So it's between 2.5 and 3 that we see this sort of drastic change. And this is then what we're evaluating. We're looking at this distance between the two major points of the elbow, and the distance between those 2 points is 0.5. Between that 3, which is where it like stops doing its weird turn, and when it starts doing it is basically 0.5. So taking that adjustment of that distance of the elbow change, we can now choose our EPS value based on that K distance graph. And now we get this, right? Is this better than the previous one? The answer is it's more accurate because the other one was obviously very false. And all that this is saying is that it doesn't think that there is a distinguishing difference between the wines from DBSCAN's perspective. Now, this is due to a number of factors. DBSCAN needs quite a few data points to figure out density. There was only 173 data points, so there wasn't enough for it to figure out a pattern unique. And this is something important to note about its sort of limitations. It couldn't find the clusters easily. It knows that pretty much all of it is the same because it's wine, but it doesn't know how to do anything. But there's still room for improvement. Unfortunately, from a data point of view now, there isn't much more we can change other than adding more data to this model, right? We can't change the EPS any better. It's locked in at 0.5. We can't scale the data anymore or differently. So generally speaking, for DBSCAN, we're done. But for K-means, it's got a good point for us to move forward with this assumption that great, 1, 2, 3 clusters. What do we do from here? So in terms of that space, let's look at the applications of K-means, because often what happens is everyone looks at the really nice graphs and they go, what do we do from there on? So from here on, we assume we performed K-means clustering properly and that we've got our labels. So with that, we basically take those 3 clusters that we've defined and we fit that to the data set. So that 1, 2, 3, whatever categories you want to call them, we're basically going to assign that to the data set. And then basically ensure that we combine the original data set with our cluster labels. And what we then get is the following. I left the DBSCAN labels in so that people can also see them. But basically the labels then produce. So 1, and if you look at the data set without the head on it, you will then be able to view a series of different values for K-means label. There are 3, right? And what we can then do now is technically we've got a predictive label, right? We can say that everything that's 1 should be red wine if we know the data set well enough. And everything that's 0.0 is going to be rosé, and everything that's 0.2 or -1, whatever the sort of value is, can now be assigned the value of red wine, whatever it is. So we now have a label. Whether it is 100% accurate, that is where the next step of this comes. So the question asked sort of from K-means versus DBSCAN and why it failed. If you look at alcohol and its sort of distributive effect, right? Does that look linear or does it look quite drastic? It looks sort of like a heartbeat. And if you can try this with each and every single column, none of the data in this data set is nicely spread out. It's not uniformed. It doesn't represent good sort of data for advanced things. It looks all, to lack of better word, random, sort of mixed matched, right? That's sort of what we're looking at now, right? Is just randomization. So this data set, while we can create clusters, there's a lot more to do. We can look at our correlation matrix again, and now we can look at how well does alcohol correlate with our K-means label. How well do all of these correlate to the class, right? Because in essence, now the class that we've created now, or this cluster, can be considered a label. And before we started, we said that there are two things that could be an effect of a wine, right? It's the color of the wine and the hue of the wine will tell us what type of wine it is, right? Right? If I put something red in front of you and I tell you it's wine, you're going to tell me it's red wine. If I put something clear and tell you it's wine, you're going to tell me it's white wine. And if it looks off color, you're going to tell me it's a rosé. So you know that. Now the model can see that too. And it correlates very well with the assumption, which means our clustering, given we found three distinct things, and those three clusters are highly correlated to the color and hue of this data set, means we're on the right track for then creating these labels as permanent fixtures. And we can go and look at sort of color intensity versus the K labels. Now, like I said, the labels are 2, 1, and 0. And you can see that sort of anything between 2 and 6 was considered a category 2. Anything between sort of 4 and 8 was considered a 1. And then the latter part was then anything from 4 to 12 from a color intensity point of view was considered to be the third grouping. So what we now need to do as analysts is go, for every single grouping, are there trends, are there patterns, and do they make sense? So you would repeat this for you would repeat this observation for basically anything that you think is relevant to the data set. So looking at this, you can go and say, well, how does alcohol compare to my three categories? Theoretically speaking, your alcohol should be very similar because all wine technically has the same alcohol levels. So you're looking for really strong different indicators to see what is influencing these sort of wine clusters that you have. Right. And sort of going into what do we do now, right, is the long process. Now, I'm not going to do it for every single one because it's the same code we're going to rework, but you would now need to go into feature comparison. So you would take each and every feature, compare them now to your cluster, read and interpret the results, and validate that the grouping looks correct. If the grouping is incorrect, for example, I would like to know why everything with a color intensity of 4 to 6 is not part of this group 1. Like, why is that the case? So maybe you need to look at color intensity and the hue to then get the true color. Maybe you need to do feature engineering to actually then, instead of looking at a numerical value, you need to add the actual color that's produced from hue and color intensity, multiply the two together to get the real color, and then see, does the real color label match the k-means label that you've created? So does everything in category 2 equal white? Does everything in category 1 equal rosé? Does everything in category 0 equal red, or whatever way it is? So that's the next step of it, is to then go and understand what does color intensity and hue mean in terms of a real color in the real world, and does that match with your clustering that you've created? Next is to go per cluster, why did the cluster form, right? So why did we form clusters 0, 1, and 2? What is the distinguishing characteristics of each individual cluster? Now, to do this, you can run a feature importance where you have your data predicting the clusters, and then you basically say, cool, what is the feature importance for everything that is cluster 2 related? What is the feature importance for everything related to cluster 1 and 0? And the last thing you would do is segment optimization, right? So we know that these groupings formed, for example, over here. Is there any reason that we can change to say, well, these data points should actually be part of the yellow sector, or this point here should actually be part of the yellow? Can we fine-tune these segments to make them more holistic? And the only way we know that is if we actually compare the color spectrum of these wines, because I think from our assumptions, these the groupings are based on the color of the wine, not the alcohol, not anything else. The clusters or the unknown pattern in this data set is just that there are 3 different wine groupings that we have in our data set, and this is what they are. So that is what this analysis would lead to, is that now if anyone gives you a data set with those indicators, you can tell them if it's red wine, white wine, or rosé, looking at this data set. So that is what you built. And what you can do in the real world with that sort of application is Basically, as long as someone's able to give you the color and hue of a certain wine, your model will be able then to predict, is it a red wine, white wine, or rosé? Right, so it becomes a classification model, but it needed to start as an unsupervised model before it becomes a classification model. All right, so a lot of sort of theory covered, or just sort of practicals of it. I'm now going to give you this link, as sort of everyone sort of asked for. It is sort of going to lie in my personal drive for now, and then you're going to get, oh, you're not saying technology, anyone with a link, right? You guys should be able to view it, access it. It will be on Athena, and like I said, your GitHub repository is almost completed, which will have all webinars that we've had, and it will have all the notebooks that we've had in one central place for you to access. And because it's GitHub, you should be able to fork it. So almost done with that, and sort of will be a parting gift soon. All right. So with that out the way, I'm going to go into Q&A, and let's see what you guys have to say. So it seems that there isn't anything we're looking at. That's just a general thing. Unsupervised is meant to be very tricky. I don't think it's an easy topic for us to sort of cover. What I do think is that this is the hardest it gets in the course from a sort of learning perspective, right? It does tend to calm down a little bit as we sort of go into AWS. So, cool. The first question is obviously Athena. We haven't put any resources on there. Yes, because it doesn't open. So unfortunately, what I noticed is that when we share the resources with you, unfortunately, the issue is that it tells you you can't access or edit the notebook, or you can't even make a copy or view the slides. So that's why we're creating the GitHub repo, so that regardless of whether you are a student or not a student, or have Google account or don't have a Google account, you can access it as long as you have a GitHub account. Or you don't even need a GitHub account because it will be public, meaning anyone can access it as long as you get the GitHub URL. So we are sorry, but we will have that up for you as soon as possible to try and get that. It's just a bit tricky correlating all the sort of data that we had from the start of the course up until now, but we will have it to you as soon as possible. Cool. After the program is complete, will we be allowed to apply for an internship program at Explore? So currently that option doesn't exist. So to do an internship, you have to come in through one of Explore's programs, which is not ALX, right? So it's a different offering, all in all, and that's the only way you sort of access the internship. However, we are looking to see if we can leverage some of the projects that are coming from the internship space and share it with you guys. So while you might not have the full support of a technical lead, you will be able to get a real project with data that you can then go and add to your portfolio. You guys can make your own mini teams. We are working out the logistics behind it, but currently now, to answer that question, no, you can't directly apply just for the internship program. You have to apply for the whole program, but hopefully we can meet you somewhere in the middle by sharing some of the projects that's happening in the space. And what we will do is going forward is invite you to our interns presentations so that you can see what they were working on, what problems they're solving, and see if it inspires you. All right, so we will look into that to see what's going on. Right. Next up, I have a question which I'm not sure how to answer. Is the process the same for structured data? So Anonymous, you'll need to explain a little bit more what process. Is it the process of like analyzing the data and clustering it? Typically speaking, yes. So unsupervised, while we often say there's no labels, the only reason you guys used the predictive variables in regression and classification is because we told you those are the predictive variables. If someone told you those are just part of the data set and it's not a label, typically it falls into the realm of unsupervised. So you can typically go through that journey throughout the thing of forming clusters, see if they make sense. And if you're good, what you can test your knowledge and skills on is you guys looked at the wine CSV already before, that one that had the wine quality metric on it. Take that column out, run unsupervised, try and create those clusters and see how well your clusters are correlating to the actual Y value. Will be a very cool way to practice your sort of unsupervised techniques and see how well you can create and form clusters. Cool. And sort of last question that I can see for now is how long will we have access to Athena course content after graduation? So currently we are agreeing to a minimum of 6 months. We'll look to see if it's extended slightly further. Currently, I think we've allowed our previous course 6 months access. So for you guys, it'll be 6 months. It might be slightly longer in sense it'll be a year that you will have access to Athena. So hopefully you then have enough time to get your resources that you need and making sure that it's saved somewhere and easily accessible later on should you need to refer back to any of the notes that occurred in the course. All right. Cool. All right, perfect. I'm just gonna look, I need to launch a poll. I don't really have a learning outcome. The outcome for today was basically a deep dive into the realm of unsupervised. So do you know why PCA and TISNI are used in essence? You know, what makes them tick, how it work? Are you able then to interpret these graphs and then basically make informed decisions going forward? Right, so notebook, like I said, is available. I did share it in chat, so you should all have it. And then sort of we'll continue this journey of going deeper into the models so that you actually understand which one you should be choosing per data set and so forth. Right, cool. Last question. Is there a reason we cannot have lifetime access to Athena? So I predict we're going to be scaling quite rapidly, and obviously we need to store students' data and information, which does become quite a lot over time. So usually from a data perspective, every 3 years they would like remove entries to make sure that we can make space for new learners to come through, because it is quite costly to scale sort of storage systems. So that's the reason it's not lifetime. That's why we can guarantee 6 months. But obviously lifetime is subjective to costs, company scale. If we magically say we need 2 million students tomorrow, we will scale, but we will also know that come a year from now, we're going to want to take all 2 million off so we can onboard the next. So it's more just from a cost saving perspective that we can't guarantee lifetime access to Athena. Awesome. Cool. Right, someone shared the link in chat. Thank you, Richard. At this point, I'm going to go, well, we were in Q&A, so I'm going to hand over to Naomi, I think, who's going to be taking you through the announcements and updates for this week. Yeah.
Yes, thank you so much, Damien, for this webinar. Unsupervised learning is actually pretty complex, but with this webinar that we've had today, I feel like the journey will be smoother. So, the updates we have for you today, this week's assignments, your K-means and hierarchical clustering MCQ, is due on Monday, 3rd of June, at the usual time, 9:59 p.m. GMT. So remember that for MCQ, one attempt before the deadline. So go through the instructions carefully and answer the questions. Um, we'll have a webinar watch party. So to revisit this webinar today, we'll have a watch party tomorrow at 2 p.m. GMT. So if you want to go through it again, not alone but with your peers, please join our watch party tomorrow. And then our next webinar is on Thursday, so come prepared so that you could get insights just like you have today. And then remember your study group discussions. Remember to interact with your fellow learners in your study groups to make this unsupervised journey easier. Um, Not to forget our support channel. Um, Sorry, Damien, can you go to the next slide? Remember your support channels, answer base for your content related questions. If you have any technical content related question or very long line of code you need the tutors to look through and guide you on, please remember you have Answerbase for that. Then you have Leah or Zendesk for the program support. So if you're not viewing your portal spaces, or if you're not able to access Adina, please remember that you have Leah and Zendesk there for you to log your queries. And then remember your community platform. Remember to go through it, um, stay updated on all the program related announcements and everything on your community platform. Interact with your peers and keep the community alive, basically. Thank you so much once again for joining today's webinar, and I'll see you in the next one.
Awesome. Cool. Thanks everyone. And sort of just a heads up, if you are in cities or in the hubs, we are welcoming the next cohort of data science and data analytics students. So if you do see any new faces, I'm sure they'll love to hear sort of your experiences on the course, or, you know, your wisdom that you might have. Don't lie to them and tell them the course is easy, please. They need to come in working very hard. So if you are going to interact with any of those students, share your thoughts with them, create a community, because at the end of the day, they'd love to hear from those that have been through the same journey. So that's it from my side. I hope you've sort of enjoyed today's talk. Until Thursday, I hope you guys have a good one. Stay safe, and we'll see you in the next one. Cheers for now. Bye.
I'm a treasure in a Lamborghini. If you're slow, try Santorini. I shall go, she should go to Aniri. The Bashale, Wama, Pua, Shani, Richard. Yeah, I'm all logo. The battery, me, Rama logo. I'm all logo. The battery, me, Rama logo.
Came from the trenches, more like to make it. No time to the talk with you, no pay me. Niggas start this money, code the ceiling. High, Kole Gara, Kole chest billing. Oh Miami, I be how you see this. Touch on Ghana, get to lock by CDs. Me, I know they fall, juicy riri. Why I know they force, they make them feel me crumble. Molo had the mission not to make it out the streets. Energy was high, I had to give myself some wings. I can't even lie, so I was stretching on my P's. Still I had to grind, I had to give myself some wings. Everything was fine till I started all this shit. Thought I had them on my back, but I guess that was the streets. Still a nigga grind, I was smoking heavy weed. That was all I had, couldn't explain on my field. Goddamn, yeah.
I'm all logo. So bad to leave me around my logo. I'm all logo. So bad to leave me around my logo. I'm all logo. So bad to leave me around my logo. I'm all logo. So bad to leave me around my logo.
Stack the money up, owó ló ṣe gbogbo. Wálé fún mọ́mí ìwà fún dáàdì máa jẹ́ kówó ṣe dòdò. Tẹ́gbọ́n mọ́ṣẹ́ ní màgà ó di dọ́dọ̀ ẹsẹ̀ àgùn. Ó máa ṣiṣẹ́ ó máa lágùn, ó dẹ̀ lè sọ àgùn dìgbà kí.